Friends, welcome Neuron Chemistry class. We are studying chapter 4 Chemical Kinetics. In this video we will discuss about the Arrhenius theory and the activation energy. Before discussing the Arrhenius theory, I will revise you the differences between the first order and second order reactions. Okay, first order reactions and zero order reaction. What are them? First order reactions means the reactions for which the rate of reaction depend upon the first power of the concentration of the reactant, means its rate law is R is equal to K1A to the power 1. While for zero order reactions means the reaction for which the rate of reaction depend upon the zeroth power of the concentration of the reactant, means R is equal to K0A to the power 0. This is the first difference, and according to this integrated rate equation, K1 for first order reaction will be equal to 2.303 upon T log A upon A minus X, while for zero order reaction it is K0 is equal to X upon T only. Unit of K for first order reaction, it is time inverse only. It may be second inverse, minute inverse, hour inverse, day inverse, week inverse, year inverse, and etc. etc. While for the zero order reaction, the K0, unit of K0 is equal to moles per liter per time, or we can say moles liter inverse time inverse. Next, half-life period or half-life time means T half. T half for first order reaction, there is no any dependence of T half on initial concentration, means T half is equal to 0.693 upon K1. T half does not depend upon the initial concentration A, while for zero order reaction, T half is equal to A0 upon A upon 2K0, means T half is directly proportional to the initial concentration A. Next, differences of graphical representation. Both the graphs are straight line, but here the graph is plotted between the log A upon A minus X and T, while in zero order reaction it is between X and T. Here the slope represents its rate constant, means tan theta is equal to del X upon del T, while in first order reaction the slope is equal to K upon 2.303. These are the some differences and comparison between the zero order and first order reaction. Now will be discuss the Arrhenius theory. Arrhenius was a scientist studied on the kinetics of the reaction and derived a relation between the rate constant and the absolute temperature. As we have discussed in the factors affecting rate of reaction, as temperature increases, the rate of reaction also increases. Even on increase the temperature of 10 Kelvin, the rate of reaction increases by 2 to 3 times. So the Arrhenius gave an equation known as Arrhenius equation. It is K, it is rate constant, is equal to A exponential to the power minus EA upon RT. Again, K is equal to A exponential to the power minus EA upon RT, where K is rate constant, A is Arrhenius constant, which depend upon the reaction. It is characteristic of the reaction also. EA, it is new term. It is actually activation energy, and very important term. R is gas constant and T is absolute temperature. Okay, the characteristics of Arrhenius theory are as follows. What are the points of Arrhenius theory? Number 1, the energy of all reactant molecule is not same but differs. Suppose there are 100 molecules in any container for reaction and to make a product. Okay, these 100 molecules does not possess same energy. Some molecules are of higher energy and some are very low energy and some are of medium energy. So there are different energy levels of the molecules. Only the molecules with high energy can make the product. So the energy of all reactant molecules is not same but differs. So the molecules having high energy can convert into product, and these molecules are called active molecules. Means what are active molecules? The molecules which can convert into product with high energy are called active molecules. Okay, active molecules maintain a minimum energy level to convert into product. This minimum energy is termed as threshold energy. What is its meaning? See, it is a graph between reaction coordinates and the temp and energy. Okay, suppose this is the graph. This is this is the level of reactants, and this is the energy level of product. Okay, and this is the path of reaction by which reaction will takes place and will make the product. Okay, when reactant are converting into product, this energy level is must to maintain the reactant molecules. Means, just like a hill, we want to go from this side to this side, we have to cross this height, and after this height we can go easily from this side. So to convert into product, the reactant molecule must have this energy level to convert into product. This minimum energy level is known as ETH, means threshold energy. This is compulsory. And active molecules means the molecules which have minimum this energy level can convert into product. Okay, the reactant molecules have minimum energy level. This minimum energy level is known as the E threshold or threshold energy. Clear? The minimum energy required to active molecules to convert into products is called the threshold energy. Clear? See, this is the exothermic reaction graph and this is endothermic reaction graph. This is the energy level for reactants and this is the energy level for product. This is the ETH for both reactions. This is the average energy level of the reactant and this is the minimum energy required to convert into product. So this energy difference of the E average and E threshold energy is known as the activation energy or EA. Okay, the minimum amount of extra energy, this extra energy required to convert the reactant molecule into product is called activation energy, or we can say the difference of threshold energy and average energy is called activation energy. Threshold energy minus E average, average energy is known as the EA. Okay, clear? Activation energy is equal to threshold energy minus average energy. EA is equal to ETH minus EAVG. Normal molecules with average energy acquire this activation energy by way of collisions among them. They collide with each other and gain more and more energy to activate and to convert into product. The rate of reaction depends upon the concentration of active molecules. Means, more the active molecules, more product will be obtained, means the rate of reaction will be more. Okay, so rate of reaction is directly proportional to the active molecules. Okay, which with increase in temperature, the concentration of active molecules increases, hence rate of reaction also increases. Okay, as we know that as temperature increases, kinetic energy also increases. As kinetic energy increases, collisions between the reactant molecules increases. Collisions increases means energy increases, and energy increases means number of active molecules increases, and number of active molecules increases means rate of reaction also increases. Clear? Thus, on increasing the temperature, rate of reaction increases 2 to 3 times. Clear? So it is the Arrhenius theory and Arrhenius equation. With the help of this Arrhenius equation, we can calculate the rate constant at different temperatures. Okay, now we will calculate the rate constant at different temperature. It is the Arrhenius equation. K is equal to A exponential to the power EA upon RT. On taking log of equation 1, we can take ln K is equal to ln A minus EA upon RT. We will convert it into log base 10. So 2.303 log K is equal to 2.303 log A minus EA upon RT. Now we will divide this complete equation by 2.303. Then the equation will be converted into log K is equal to log A minus EA upon 2.303 RT. It is the another form of the Arrhenius equation. We can use this equation as well as this equation also. This equation is used to calculate the activation energy of any reaction. Okay, now assume that rate constant of any reaction at T1 and T2 Kelvin temperatures are K1 and K2. Reaction is same but temperature is different, so the rate constant are also different. So according to Arrhenius equation, first condition, log K1 is equal to log A minus EA upon 2.303 R T1. This is T1. And for T2 temperature, log K2 is equal to log A minus EA upon 2.303 RT2. There is no any A1 or A2 because reaction is same. For same reaction, the value of A will remains constant. Okay, now will we subtract the log K2 minus K1 because T2 is high temperature, means the log value of K2 is high. At high temperature, rate constant also high. So log K2 minus log K1 is equal to log A minus EA upon 2.303 RT2 minus log A minus EA upon 2.303 RT1. Okay, log A is cancelled by log A because it is positive and it is negative. On solving these brackets, log K2 upon K1. Okay, we can write log A minus log B is equal to log A upon B. I have told you already in last videos. So log K2 minus K1 means log K2 upon K1 is equal to EA upon 2.303 RT1 minus plus minus EA upon 2.303 RT2. Here EA upon 2.303 R is common. So the equation becomes log K2 upon K1 is equal to EA 2.303 R 1 minus T1 minus 1 upon T1 minus 1 upon T2, or we can say that log K2 upon K1 is equal to EA upon 2.303 R T2 minus T1 upon T1 T2. This equation is used to calculate the activation energy or the high temperature or the rate constant of the reaction. Thus, knowing the value of K1, K2 and T1, T2, the value of EA means activation may be calculated. We can also calculate the value of EA by graphical method. One more method to calculate the activation energy is graphical method. Okay, we know this is the Arrhenius equation, second form of the Arrhenius equation, that was log K is equal to log A minus EA upon 2.303 RT. We can also write this equation in another way, like log K is equal to minus EA upon 2.30 RT plus log A. The sides are changed. This equation represents the right straight line of the form y is equal to mx plus c. So as we plot the graph between log K and 1 upon t, we will obtain a straight line. This. Okay. If a graph between log K and 1 upon t is plotted, then a straight line is obtained with slope. Its slope, this theta slope, gives minus EA upon 2.303 R. This value is obtained from the slope, and this value will obtained from the intercept of the graph. So intercept shows the log A, and its slope shows the value of minus EA upon 2.303 R. The R value of R is well known. It is a gas constant 8.314 joule mole inverse Cal inverse. So we can calculate the value of EA also. Clear? Now we will discuss the role of activation energy in chemical reaction. What is the role of activation energy? What happens if activation energy is less or more? It can be explained by the example of catalyst also. Explain that the presence of catalyst affects the rate of reaction. As we know that in the presence of catalyst, the rate of reaction is more and more, is increased by many times. Okay, why? This is due to the new path of catalyst. The catalyst provides a new path for the reaction with lower activation energy. So it enhances the rate of reaction. What it means? See, this is the normal equation. It is at energy level and it is reaction coordinates. It is the normal reaction in absence of catalyst. This is the average energy of reactants. It is the average energy of product. It is the threshold energy and it is activation energy. In the absence of a catalyst. In the presence of catalyst, a new path is provided. In this new path, this ETH is minimized, and due to ETH minimized, the activation energy is also decreased. EA dash is very less than EA, means activation energy is very less than the activation energy in absence of the catalyst. So it is easy to convert the reactant particles into product particles. So as activation energy is less, then rate of reaction is more. Means we can say that the lesser the activation energy of reaction, then reaction will be faster and vice versa. Means rate of reaction is inversely proportional to activation energy. Means if activation energy is more, the rate of reaction is less, or we can say activation energy is less, rate of reaction is more. The Boltzmann Maxwell energy distribution curve, very important curve and very small thing, very easily the Boltzmann and Maxwell describe that why the rate of reaction increases by 2 to 3 times on the increase of temperature, increase in 10 Kelvin or 10 degree Celsius. Okay, they plot, Boltzmann and Maxwell plotted a graph between the kinetic energy and the fraction of the molecules having sufficient energy, and this graph is known as the Boltzmann Maxwell energy distribution curve. So this is the graph. Here it is kinetic energy and it is the fraction of molecules. These molecules show very low energy. Okay, these molecules show the maximum these energy, and this is the maximum energy of the maximum molecules. It is also known as the maximum probable energy of the molecules. Okay, this is the most probable kinetic energy. Okay, it at T1 temperature. It is the ETH. It is the threshold energy. It is the minimum energy required to reactant into product. So only these molecules, these less number of molecules, this is can convert into product, because only these molecules have the energy more equal or more than the threshold energy, and these molecules cannot convert into product. When we increase the temperature of the reaction by 10 Kelvin, then the graph is flattened and expressed to the right side. Means when temperature is increased, then the kinetic energy of the molecules increase. As kinetic energy increase, I have explained just before the time that kinetic energy increases, then the number of collisions between the reactant molecules increases. As collisions increases, as the activation energy easily obtained to the reactant molecules, and they cross the ETH or threshold energy and can easily convert into product. So at by the increase that of 10 Kelvin temperature, the number of active molecules becomes 2 to 3 times. This is the T Kelvin temperature number of active molecules, and this is the number of active molecules at T1 plus 10 Kelvin. So number of active molecules is increased by 2 to 3 times. So the rate of reaction is also increased by 2 to 3 times. By this way, Boltzmann and Maxwell explained that why the rate of reaction becomes 2 to 3 times at T plus 10 Kelvin temperature than the T Kelvin temperature. Clear? Thus, I can explain the change in the rate of reaction as temperature by the help of Arrhenius equation and by the help of Boltzmann-Maxwell energy distribution curve also. I think you can understand these two main concepts by this video. Thank you.